A deep dive into sklearn's ExtraTreesRegressor. The ExtraTreesRegressor in scikit-learn sklearn is a powerful ensemble method for regression tasks. It builds upon the principles of random forests, introducing extra randomness during tree construction to further boost model performance and reduce overfitting. Here's a detailed breakdown. 1. Core principles. Ensemble learning like random forests. ExtraTreesRegressor relies on the wisdom of the crowd. It constructs an ensemble of multiple decision trees, each trained on a different random subset of the data. The final prediction is the average of the individual tree predictions, making the model robust and less prone to individual tree errors. Random subspace during tree construction. ExtraTreesRegressor randomly selects a subset of features for each split, further promoting diversity among the trees. Extra randomness. Unlike random forests, ExtraTreesRegressor introduces an additional layer of randomness by randomly choosing the best split point from among a randomly chosen subset of possible split points. This prevents individual trees from becoming too specialized to specific features or data patterns. 2. Algorithm steps. 1. Data preparation. The training data is split into multiple subsets. 2. Tree construction for each subset. Feature selection. Randomly select a subset of features. Node splitting. Randomly select a subset of possible split points. Determine the best split point within this subset based on a chosen criterion, e.g., Gini impurity for classification or mean squared error for regression. Tree growth. Repeat step 2 until a stopping criterion is met, e.g., maximum depth, minimum number of samples per leaf. 3. Prediction for a new data point. Each tree in the ensemble makes a prediction. The final prediction is the average of all individual tree predictions. 3. Key advantages. Robustness. The ensemble nature makes the model less sensitive to outliers and noisy data. Low variance. The randomness during tree construction reduces overfitting, resulting in models that generalize well to unseen data. High accuracy. The combined wisdom of multiple diverse trees often yields highly accurate predictions. Feature importance. ExtraTreesRegressor can be used to identify the most influential features in a dataset, providing valuable insights. 4. Parameters and hyperparameter tuning. Nestimators. Number of trees in the ensemble. Higher values generally improve accuracy but increase computation time. Criterion splitting. Criterion used to evaluate the quality of splits, e.g., MSE, MAE, max depth. Maximum depth of individual trees limits the complexity of individual trees and helps prevent overfitting. Minsamples. Split. Minimum number of samples required to split an internal node. Minsamples. Leaf. Minimum number of samples required to be at a leaf node. Max features. Number of features to consider when looking for the best split. Bootstrap. Whether to use bootstrapping to sample data. Default is true. Random state seed for random number generation, allowing for reproducible results. Tuning these hyperparameters is crucial for maximizing model performance. Techniques like grid search CV or randomized search CV can be used to find optimal parameter values. 5. Applications. Regression problems. Predicting continuous values, such as house prices, stock prices, or customer churn rates. Feature importance analysis. Identifying the most relevant features in a dataset, aiding in feature selection and understanding data relationships. Handling high-dimensional data effectively. Dealing with datasets with a large number of features. 6. Caveats. Interpretability. While robust, ExtraTreesRegressor can be difficult to interpret due to the complex ensemble nature. Computational cost. Building a large ensemble of trees can be computationally expensive, especially for large datasets. 7. Example. Python. From sklearn, ensemble import ExtraTreesRegressor. From sklearn, datasets import load Boston. From sklearn, model selection import train test split. From sklearn, metrics import mean squared error. Load Boston housing dataset. Boston load Boston. X Boston. Data. Y Boston. Target. Split data into training and testing sets. X train. X test. Y train. Y test train test split X. Y. Test size 0.2. Random state 42. Create ExtraTreesRegressor. Regressor ExtraTreesRegressor estimators 100. Random state 42. Train the model. Regressor. Fit X train. Y train. Make predictions on test set. YPRED regressor. Predict X test. Evaluate model performance. MSE mean squared error test. YPRED. Printf mean squared error MSE. Conclusion. ExtraTreesRegressor is a powerful ensemble method that combines the strength of multiple decision trees with extra randomness for improved robustness, reduced variance, and often high accuracy. Its ability to handle high-dimensional data and provide feature importance makes it a valuable tool for various regression tasks. However, careful hyperparameter tuning and an understanding of its limitations are crucial for optimal performance.